This is for test corrections. Finally got the remarkable working. That's exciting. It works really good. So let's continue. First question says that I need to analyze the function y equals x squared times e 1 over x squared. So the first thing I need to do is graph the equation on my calculator, and I should get something a little bit like that. And if you look at this, from about right here to right here, it's decreasing. And from right here to right here, it's increasing. And then decreasing, and then increasing, right? So once I graph that and look at this, the next thing I need to do is go and do the product rule for this equation. So that should get me, for the derivative of y, x squared, so the first one, and then I'm going to find the derivative of e to the power 1 over x squared. But pretty sure I'm going to use chain rule for that. Is I'm going to do e to the power 1 over x squared times the derivative of 1 over x squared. And then I'm going to, part of the product rule, I need to add this to the first one, so the e 1 over x squared times the derivative of x squared, which is just 2x. Alright, now that I got this, I need to find the zeros of this equation. So in order to do that, though, if I look at this, I see that I can simplify this down and get e 1 over x squared out of there, because it has a common factor in this and this side. So what I can do is I can go like this. 1 over here. So I put e 1 over x squared times negative 2 over x plus 2x. Boom. Yep. And if you look at this too, when you take this one right here and you multiply it to this one, it gets rid, the exponents add, so it just gets to negative x, negative 2. And since negative x, you can move that down to the denominator and make that 1 over x, or negative 2 over x. And then that's it for the simplified. So now I can, now I need to equal this to 0 to get the zeros of the function, right? And if I look right here, I know that this will never equal 0, right? So I set this part right here equal to 0. And then in order to find common denominator, I believe I need to multiply this right here by x to get the common denominator. Yeah, 2x squared over x. The x's cancel out because you can't really do the denominator of a function. It's just the numerator. So you just get to 2 plus 2x squared, right? And then what you do after that is you add the 2 to both sides, and then you get 2 equals 2x squared. Then you divide by 2, which just gets you 1. So then you got 1 equals x squared. And we already know the square root of 1 is just 1. So we know that 1 plus or minus equals x, right? So now I know that the critical point here and critical point here are at negative 1 and 1. Alright, moving on. So for a in this equation, it says find the intervals on which the function is increasing. So, and when I look at the graph, right here, there's like an asymptote going to this way, right here, and right there, there's asymptotes. And so, from the function where it's increasing, right here, it's going from negative 1 to infinity, right there, right? Or negative 1 to 0. And then, negative 1 to 0 is where it's increasing because it's getting closer and closer to 0. And then from 1 to infinity, it's increasing on this side, right? So for a, when it asks us find where the function's increasing, it increases at it increases at -1 to 0 and 1 to infinity. Right? Alright, so that's the answer for part A of this problem. Part B asks us to find the intervals on which the function is decreasing. Now, looking at this again, you can see the function is decreasing from -infinity to -1, and from 0, because this asymptote's this line right here, asymptote, is approaching 0, 0 to 1. So B would just be it decreases at -infinity to -1 and 0 to 1. Kind of like the opposite of part A, right? So now that I got that, I move on to part C. Part C is asking me find the intervals on which the function is concave up, right? And so by looking at the graph, I can see that from -infinity to 0, because it approaches to 0 right here, approaches 0, and it just goes on forever in -infinity direction. Same thing on this side with positive infinity. The concave up is from -infinity to 0. On the other side, it sounds kind of weird, but it's from 0 to positive infinity. So the answer for C is that by looking at the graph, it's -infinity to 0, again, because there's an asymptote at 0, -infinity forever, and 0 to infinity. Right, that's part C of question 1. Alright. Part D of question 1 says find the intervals on which the function is concave down. Now, also, by looking at the graph, you can tell that there is no concave down points, because, I mean, there's both two concaves ups. So there's, for D, it's just simple, none. No concave down at all. Question E says find local extrema. Well, to find local extrema, I have to plug -1, this answer right here, I have to plug this answer into the regular y equation. That one right there. So for the first one, when I do -1 for x, I plug it into as x. -1 times -1 equals +1. And then so for, yeah, this right here is here. Let's actually set it out here. Y equals -1 squared E1 over -1 squared. So I look at this equation. This right here is positive, so y equals 1 times actually, I don't need to do that. Starting note, it's 1, I don't need to write it down. So E time e to the power of 1 over -1 squared. -1 squared, as we saw here, is just 1. So e to the power of 1 over 1 is just e. So for y, we got e. So one of the local extremas is at -1 e. It doesn't really matter your answer. You're always going to get e for y, because they're both just 1. It's not going to change anything. Unless it was a cube root, it would change something. So I know that at -1 e, it's e. So -1 e is one of the extremas, and just +1 e is the other extrema. So there's answer to question E. Now question F tells us to find any inflection points. And the answer to that one is there's no inflection point, because there's no change in concavity, meaning that it never goes from being concave up to being concave down all of a sudden. It always just goes concave up, asymptote, concave up. So for F, the answer is no inflection point. Says to use mean value theorem to find the point C at which f prime of C equals f of B minus f of A over B minus A for the function f of x equals natural log of x minus 1 on 2 to 4. So first of all, I need to find f of C, which is just the derivative of f of x, which is just the natural log formula. Is since x minus 1, the minus 1's a constant, you don't get rid of that, so it's just 1 over x minus 1. So the first derivative of f of x equals 1 over x minus 1, right? So the next thing I need to do is I need to find f prime what f prime of C equals for this equation right here. And B would equal, hold up, I'm going to do that because it hurts my brain. B would equal 4 and A would equal 2. So I first plug this in. So first of all, I need to find f of B, which is just plugging 4 into this equation right here. And when I plug it in on my calculator, the natural log of 3, I should get a really ugly number, very, very big number. It should be like about 1.0986, something like that. And then that will be minused by when you plug 2 in for x. So the natural log of 1 then would be 0, right? And that would all be over b minus a, which is 4 minus 2. And that equals f prime of C. Ooh, forgot to write that in there. And so this should equal I'm going to fix that there, 1.0986 over 2. All right. So then what I do is I divide this, and it should get me about down to 0.5493 and 1. So now what I do is I set this right here equal to this equation right here. So I got 1 over x minus 1 equals, well, gosh, I keep on forgetting to do this, 0.5493 and then 1. So first thing I need to do is I need to multiply each side, I need to multiply each side by x minus 1, which then gets me to about 0.54931 x minus 0.54931, which equals about 1. Now I add this to each side, 0.54931, and then after I do that, I get 0.54931 is about 0.54931x. I just divide 0.5431 on 931 on each side, and x would then, this would be 1.5439 because I'm adding it to 1. Almost forgot. That would have been bad. So then that is what C would equal. So that is the answer to question 2. That's how you do question 2. So now it's time to move on to question 3. Okay, so for question 3, it asks me to sketch a graph of a differentiable function y equals f of x that has the given properties of f prime of negative 1 equals f prime of 1, which equals 0. F prime of x is more than 0 on negative 1, 1. F prime of x is less than 0 for x when it is less than negative 1. And f prime of x is more than 0 for when x is more than 1. So first thing I look at is right here. This sucker right here. Because those are 0, I know this right here is extrema. Right? So I have extrema on negative 1 and 1. Somewhere along this y-axis on both of them I have extrema. Okay, so since I know these are extrema, right there, boom. Since I know this right here is extrema on negative 1 and 1, right here tells me that, well, when f prime of x is more than 0, the function's increasing. So that tells me that it's increasing from the point in between the points -1 and 1. So it's increasing. And then on f prime of x, when it's less than 1, that tells me it's decreasing. So, oh shoot, I did not mean to write that. That means that when x is less than 1, so on this side of the x, -1, it is decreasing. And I know it's decreasing down to this because it's decreasing right here and then increasing. And if it helps me a little bit actually, if I number these in order. So this is 1, and then this is 2, then this is 3. So first it's decreasing all the way down to here. And I don't want to draw it up here because I have all this space to draw. So I'm going to make my point like right here. And I know it's decreasing right to here, and it levels out right there. Now, 2, I know it's increasing from this point. I'm going to make it right here. It's increasing from this point to this point, and then it kind of comes up, right? But hold it right there before I draw any more. Look at this again. F prime of x is more than 0 for when x is more than 1, meaning it's positive. It's positive on this side. What does that mean? It means that it doesn't curve. It just keeps on going up. So it's kind of like almost like an S. My graph is gonna come level out right there. See, and then it's gonna kind of come right back up here again. Boom. So this graph right here is my final answer for question 3. Alright, so for question 4, it asks me to use the derivative of y to find local extrema in any points of inflection. Y, and it gives me the equation y equals x minus 1 squared times x minus 2. Very simple. So the first thing I notice about this equation is that the critical points are pretty much already given to me, which is just +1 and +2. The critical points are x equals +1 and 2. Boom. But the first thing I do to find the critical points after doing that, establishing the critical points, is I got to find the second derivative. So the first thing I do here is I expand. So y prime equals x minus 1 squared. First, I expand this. This is probably the most important thing to expand first. So I got, I'll lower that down so it doesn't get confusing. I got y prime equals x squared minus 2x plus 1 times x minus 2, right? So I do for expanding. And then after this, I expand even more by multiplying this times this expression. These two expressions times each other. Which, when I multiply all these, it should come down to x cubed minus 2x squared plus x minus 2x squared plus 4x and -2. After that, I simplify it down from there, and I should end up getting x cubed minus 4x squared, because this one right here and this one right here, they subtract each other. They don't cancel out because they're both minus. And then I do plus 5x, because 4x plus x, plus 5x minus 2. Alright, now what I do is I find the double derivative of this equation right here. This one I find the double derivative by just using the power rule. That's pretty much it. The double derivative of this equation will be 3x squared minus 8x plus 5. Alright? And then the next step after this is I need to set y equal to 0 to get the extremas, right? So when I make this equal to 0, I need to factor this. So what I do is I come over here. Well, I need to set this equal to 0 first of all, before I factor. Squared minus 8x plus 5. So when I factor, I do the x thing right here, where it's a times c over b. So when I plug this in, I got -8. If 5. I need to add to get this, and multiply to get that, right? So negative 8 and 15, because 5 times 3 is 15. And so on this side, I get negative 3 and negative 5, because the negatives cancel out when they multiply, and they add when they're added, you know. I should get 0 equals 3x squared minus 3x minus 5x plus 5, right? And so what I do is I pull out like terms. All right, so for this first one, I could just group these together, right here, and right here, and right here, and right here, because they both have 5s. So I can do 3x right here, 0 equals 3x, and then all that is right here is just x minus 1. Boom. And then I subtract this from, I'm just gonna stick to 5, and then x plus 1. Boom. Right there. And then when I come over to here, when I do this now, I make this equal to 0, or will I just solve for 0, right? And because these are the same, these right here will just get the same output, so I can just cancel that out. And then I can group these together differently, where it's 3x minus 5 right here, and then times x minus 1. Boom. So now that I got this, I just got to plug in, make y equals 0 to each of these individually. So 0 equals 3x minus 5, and 0 equals x minus 1. This one right here, this equation is simple. It's just 1. 1 equals x, because I add 1 to both sides. So you just got to add 5, and then 5 equals 3x over 3. So 5 over 3 equals x. Okay, so those are inflection points. And so, since they're both inflection points, since there is no concave up or down and only inflection points, there is no extrema at 1. 2. I plug 2 into y double prime to see if it fits a minimum or a maximum. I have to plug 2 in for x in the second derivative equation. And when I plug 2 in for x in the second derivative equation, this equation right here, I get 2 to the power 2, 4. That is 12 minus 16. 12 minus 16 is 4, and then plus 5. That's positive 1. That means that there is a relative minimum, because it's more than 0, relative minimum at 2. So, relative min at 2. Alright, so question 4 wants me to find the dimension of the box, and you find the dimensions of the box when the box has the largest volume, and what is the volume of the box. So what I do first is I establish with this box the dimensions, and right here, these dotted out lines, they are dotted out because that means that's where you cut. So you got like the 8-inch side right here, boom, boom, 8 inches, right? And this right here, boom, boom, is 15 inches. And each of these little dots, x, 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 these are all the same length, every single side, all the same length, right? And so when I look at this box right here, I'll make a different kind of model. When I look at this box like this, boom, 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 right there, I got x. This right here is 15 minus 2x, because it's 15, 2x on each side. So 15 minus 2x. And right here, from this right here, it's 8 minus 2x, because it's minusing 2x from each side. So 8 minus 2x. Right, boom. So with these points, I can conclude that the volume equals x, the height, times the base, times the width, right? So times the height, x, times the width, which is 15 minus 2x, times the length, which is 8 minus 2x. Boom. So step 1 of this is I need to expand this, right? So I can be able to calculate the derivative easily, because this would be a little bit complicated to calculate the derivative of. So when I expand, I multiply x into this equation. So we got 15x minus 2x squared times 8 minus 2x. And then I expand these two together by multiplying this expression times this expression. So volume equals 120x minus 16x squared minus 30x squared plus 4x cubed. Alright, then I can simplify this down, combine like terms, right? Oh, which this should equal 4x cubed minus 46x squared plus 120x. Alright, step 2 is I need to calculate the derivative of this equation right here. And in order to do that, I just got to use a lot of power rule, right? So when I use the power rule for this one, when I calculate the derivative, first I'm unlining this one to box this sucker up, because this is important. So for power rule on this one, we got 3 times 4, that's 12, x, 3 minus 1, 2, minus 2 times 46 is 92, and 2 minus 1 is just 1, so it's 92x, plus 1 times 120 is just 120, x minus 1 is 0, x power 0 is just 1. So this is my derivative equation. Now, because I can't factor this, because it's impossible to factor this equation, I have to use a quadratic formula. And the quadratic formula is, by definition, x equals negative b plus or minus the square root of b squared minus 4 times a times c over 2a. Boom. Right? And so I plug in these numbers. This is a, b, c, bada bing, bada boom. Right? We do x equals negative 92 plus or minus negative 92 squared minus 4 times 12 times, oh geez, it's going to be a big number, 120. All of this over 2 times 12. Alright, so when I square this and then I multiply all these together and subtract when I square negative 92, the negative cancels out, and I should get 8,464 for this one right here. And I subtract that from 5,760, which in the square root should get me also these negatives, they cancel out, so that's just the negative times negative makes positive. So I got 92 plus or minus the square root of all these come together to make oops, wrong number. Yep. 2,704 over 24. Because 2 times 12 is 24. And then I simplify, before I simplify that any further, actually, wait a minute, I can't simplify that further. I can square root this, and that should get me 92 plus or minus 52 over 24. Okay. And so what I do first is I come over here and I make and then I solve for x. So the first time I solve for x, I add 92 plus 52. And the second time I subtract. So x equals 92 plus 52 over 24. That equals x equals 144 over 24, which makes x equal 6, right? And then for my second one, x equals 92 minus 52 over 24. Well, when I minus 92 to 52, I get 40. Right? And then from 40 over 24, I get a 40 divided by 24, I get about x equals 5/3. And the only problem is when I plug 8 minus 2x with 6, that's impossible because you can't have a side with negative inches, right? So 6 cannot be it because 8 minus 2x, 8 minus 12 would be 4. You can't really have negative 4 inches because I've never heard of that existing. So this point right here is mucho importante. I think that's Spanish. Anyways, so in order to find the dimensions now of this box, I take this formula and I plug x in for 5/3. So, well, for it just in this part, so 5/3 times 2 is 10/3. So 15 minus the answer is 35 over 3, right? So 15 minus 2 times 5 over 3 equals 35 over 3, and 8 minus 2 times 5 over 3 equals 8 minus the answer is 15. No, it's not 15. That's wrong. I don't know what happened there. Okay, so 2 times 5 over 3. Okay, then 8 minus the answer. Okay, so this should get me 14 over 3, right? So the dimensions, by looking at these, I can conclude that the dimensions, so for the height, it's 5/3 by the width, which is 35 over 3 by the length, which is 14 over 3, which also is the same as 1.6 repeating by, I need to put inches because you gotta make sure you put your notation because it's a real life problem. Inches by 5 over 3, 11.6 repeating, 0.6 repeating inches by 4.6 repeating inches. Boom, boom. That is the dimensions of the box right there. This is dimensions. All right. Now, for the last part of this problem, I need to find the maximum volume for this. So what I do is I plug in x for this one, all the x values for this. So I got the volume equals 5/3 times 15 minus 2 times 5/3 times 8 minus 2 times 5/3, right? So volume equals 15 minus 2 times 5 over 3. We already discussed that. That's 35 over 3. So 5/3 times 35 over 3 times, and 8 minus 2 times 5 over 3 is 14 over 3. And when I add these all together, I should get about 90.74, wait, just 90.7, because it only wants me to round to the 10th. 90.7 inches cubed. Alright, so for question 6, it says, use differentials to estimate the error in the area of a circle with a radius of 10 plus or minus 0.1 inches. Express the answer to the nearest tenth. Alright, so the first thing I need to do is recognize that the area equation equals pi r squared, right? And in order to find this, I have to find the differential of dA, because, well, yeah, I'll get to that later. So dA over dr equals 2 pi r, and it's just 2 pi r, not 2 pi r squared, because power rule. Boom, 2r, 2 times r, and then 2 minus 1 is 1, so it's just r. So 2 pi 2r, but it looks nicer when you're at 2 pi r, right? So what I do next is, after this, I multiply the dr on both sides. So dr times this side, dr times this side. So I end up with dA equals 2 pi r times d, oops, that's an uppercase d, dr. And then after this, I plug 10 in for the radius in this equation. But because it's in the error zone area, the estimated error is plus over or under 0.1 inches. That is the dr. The dr is 0.1 inches, and the r is 10. So I plug for dA equals 2 pi times 10 times plus or minus 0.1, right? So 2 times pi is about 6.3 if we're going to the 10th, and then that times 10 is about 62.8 if we're rounding to the 10th. 62.8, right? So dA is about that's a rough about 62.8 times plus or minus 0.01. All right. So the final part is I multiply this times right here. It doesn't matter if it's plus or minus. It's just showing room of error. So it's not like when you're like making something equal to 0, when you're trying to find x intercepts or something like that. With this one, it's just how far, how in or close, like how much of an error do you have. So I just multiply this by 0.01 pretty much. So dA, this will give my answer. Ooh, the nice one. dA is about 6.3 inches, I believe. Yeah, about 6.3 inches. All right. 6.3 inches squared, I believe. No, I'm just going to stick with 6.3. The answer is 6.3. The answer is 6.3. Okay. That's the end of this question, and that's the end of the test review thing.